welcome you all to this lecture on conditional GAN to synthesize OCTA images from the fundus images. Actually, we are myself, Dr. Raja from Veltech University, and Dr. Sambat Kumar from my Veltech University and EC department. We are participating in the IEEE's Generative AI Hackathon, where we are developing generative AI based application to synthesize OCTA images from fundus images. So I would like to show you the sample of OCT and the fundus images. So these are the fundus images. Those who are having the background on medical image processing might be knowing these are the fundus images, a very simple imaging modality. Modality is OCTA, as we can see in the screen. Fundus and the corresponding OCTA, taking the anatomy, same anatomy, and acquiring the images of the same anatomy. Fundus being a cheaper imaging modality where we can see the optic disc and the blood vessels, uh, a shallow vision of the blood vessels we can see. Whereas when we go for the OCTA, it is an advanced imaging modality where we can see the depth resolved blood vessel maps. Actually, it eliminates all the other anatomies. So when I discussed with the doctor, he told that both hold complementary information in diagnosing diseases like diabetic retinopathy and age-related macular degeneration. So our idea, so far, doctors have been using fundus mainly for diabetic retinopathy diagnosis, and if they want additional information, they can go. The highly developed hospitals, they will be having the OCTA imaging modality. The cost being 20 lakhs, around 25 lakhs. Whereas the fundus image, if you see fundus camera, if you see the cost of the device is around 3 to 4 lakhs. Okay. So we are exploiting the computational power of generative AI, where we are training the generative adversarial networks with OCTA and fundus paired images, and we are trying to synthesize OCTA images for newly acquired fundus images. So that is what our project is. So we know the power of generative AI. So with the power of generative AI, instead of generating specific images, we are trying to generate paired images. Not exactly generating paired images. If we give one modality, we should be able to generate another modality. Already there have been some projects successfully completed with synthesis of CT images from MRI images or MRI images from CT images. So these are going to be benchmarking in the future, where we can expect the hospitals to have only one imaging modality where they will be able to generate the further modalities without the availability of the second device itself. Okay. So that's what one of the projects we have taken, and we have gone to the extent of developing a user-friendly app. We are running the code in Python, whereas when we go to the doctors, they cannot run the Python code and all. So we are trying to develop. We have developed a user-friendly software application, not in public domain, in local host. We are to that level we have come. So the doctor will be having a front-end interface where he can upload a fundus image and seek the OCTA equivalent. Okay. So likewise, we are working in this project, and we have been making this paper where myself and Dr. Sampath Kumar have worked in different parts of this particular project. We being completely with engineering background, the medical inputs are given by Dr. Kaushik from Vasan Eye Care, and of course, Ishuru Srinadira is our project mentor from the IEEE hackathon side. So we are working as a team, and we are very happily developing the project of synthesis of OCTA images from fundus images. As I told you, we are developing this project for diagnosis of diabetic retinopathy. So fundus image will be given as usually as one of the inputs to any convolutional neural network to identify diabetic retinopathy. So what we are extending is the second modality we are generating through our BVAC GAN, blood vessel adversarial GAN, conditional GAN. That's what we are developed, and that will develop the second modality called OCTA. We are supplementing the second modality in the diabetic retinopathy diagnosis process, where we have the ResNet 50. We are taking the ResNet 50 two times, and finally at the decision level we are combining the layers, and finally the outcome will be whether the diabetic retinopathy is there or not. Okay. So the main aim of our project is to generate a conditional GAN. GAN being generally generating synthetic images, conditional GAN generating given one modality developing another modality. That is what is conditional GAN. So that's what is the block diagram given here. And the generator of the particular conditional GAN is a unit. So this entire block was done by Dr. Sampath Kumar, the coding part, and we have made some novelty also, like using entropy based thresholding. So when we want to preserve the blood vessels, we want to preserve the blood vessels. I have thought like entropy will be the perfect parameter to preserve the blood vessels, and that have given suitable outcomes also. Okay. So this is the entropy of the actual image, entropy of a small portion taken from a small portion of the image, a tile of an image, where the entropy is 7.6. If we go for a general GAN, how much it is preserving, and our GAN, that is blood vessel adversarial loss we have defined. Based on that loss, we are able to much better preserve the finer blood vessel details. We call it as the doctors call it as a microvasculature, micro level blood vessel trees formation. So those things our GAN is able to preserve much, because the synthesized modality is going to be OCTA. We need to concentrate on the fine details. So we have gone for the, in fact, squeeze and excitation. So the coding part of these things is everything is done by Dr. Sampath Kumar. And okay, so let me see what is a GAN and what is a conditional GAN. Let me take some few minutes for those who are newly understanding what is by generative AI itself. So generative AI is something where we can synthesize data. So previously, AI has been restricted to decision, to identify something, to identify or to classify as normal or abnormal, or to diagnose something. Once the generative AI came into picture, we are able to generate data. That's what we are seeing here. We are able to generate human faces. We are able to generate medical images, original, as you can see in the top, original cerebral images are there, and GAN generated images are there, and experiments and publications are going on, very interesting, that they are giving the images, original images and synthesized images to doctors. Somewhat they are able to identify the synthesized images, and sometimes doctors also not able to identify which are synthesized and which are original images. So likewise, generative AI is making a benchmark in generating data. And what we see in the bottom is MRI and CT. So this is what is conditional GAN. The difference between general GAN and conditional GAN is, in conditional GAN, if we give both the modalities or as paired data and train them, so we cannot give completely irrelevant data. So those two should be from the same anatomy, and those should be from the same domain. So we cannot give a image from a visible spectrum and IR spectrum and call that as a paired data. It is not exactly paired data. So from the same domain, if we are acquiring the images from the same patient at the same time, the same anatomy, only with the two different cameras, we are acquiring the images in same spectrum. And those two images will be a complement of each other. MRI will be having some data and CT will be having some data. So we will be able to supplement. Uh, and once we train the conditional GAN using these two, and then later when we give the first modality, the conditional GAN will be able to generate the second modality. That is what is the idea behind the conditional GAN. And coming to the general discussion about the generative adversarial network, as I told, just two different neural networks acting in competition. So a generator and a discriminator. What a generator will do is, it will receive samples, it will receive noise from the latent space, and initially it will be generating data that is looks like a noise. Whereas here we'll give the real samples. The real samples will be given, and here some noise will be coming. The ultimate aim is the generator should generate data that resembles the real samples. So initially this looks like a noise, and this is the original image, and discriminator will be successful in discriminating which is the original image and which is a noise. Later what we do is, we try to fool the discriminator by modifying something, so that we will discuss later. What is done is, the generator will start generating images that look like the original image, the discriminator, so that the discriminator will not be able to discriminate between which is real sample and which is the synthetic sample. That is what is about your generative adversarial network. And coming to conditional GANs, conditional generative adversarial networks. So here we are talking about the images and labels. So original image, and the original image corresponds to 1, and synthesized image corresponds to 0. So likewise we are taking with the labels. Here when we come to the conditional GAN, the label will be taken to another imaging modality. So I think we are able to understand. Here the original image will be the fundus image, whereas its corresponding label will be a OCTA image. There, in the general GAN, we told the original image will be taken as 1 and the synthetic image will be taken as 0. But here what we do is, mapped paired image as its label. So that is what is a modification we are making here, and that is called as a conditional GAN. When we look at the diagram, here also the same generator and discriminator is there. Initially, the generator, instead of giving latent noise, we are giving as a fundus image. Why? Because it is acting upon two modalities, and particularly from the fundus image, it is going to generate the OCTA image. So fundus image is given as one of the inputs to the generator, and it will generate a synthetic OCTA image. Whereas a discriminator will receive also the real OCTA image. The success of the discriminator is to distinguish between real OCTA image and synthetic OCTA image. We play with the loss functions and we fool the discriminator, and that is what we are going to see as a coding now. But as you can see in the screen, this is a front-end Jupyter notebook, and we are importing the drive in the first step. As we have the input data in the drive, we are loading the data from the drive, that is the original fundus images, and what needs to be synthesized to train the GAN, mapping the images from one modality to next modality. One is mapped to one here. So fundus images mapped to the OCTA. Those training are being done. It is already available on the internet. The dataset is not developed by us. So we have the train A, train B, test A, and test B folders, and those are being called from the particular Google notebook. So here we have the options to connect to the Google. Okay. So first we are importing the Google Drive. My Google Drive we are importing, and we are installing the necessary libraries. TensorFlow we are installing. TensorFlow examples, TensorFlow examples.git we are installing. So some of the functionalities like pix to pix unit, those are available in the TensorFlow examples. So whichever necessary modalities and necessary libraries we are installing and installing. Okay. So next we are importing TensorFlow and other libraries, importing time to calculate the time of the algorithm run, and all these things we are importing. And we are having this particular modality like physical devices. So how many GPUs are available when we are running? So we in fact purchased the Google Colab is batch size, in how many batches we are running the code, and what is the size of the image, number of rows and columns, these are being displayed here. So I will rush up the sequence coding and come to the main coding faster. And we can see here random crop. The images are randomly cropped. Squeeze means one of the dimensions will be removed. For example, in TensorFlow you could have seen none comma 256 comma 256 comma 3. That means the size of the image is 256 by 256 by 3, whereas that one is nothing but the initial none, or one is nothing but the channel. So we want to squeeze that, we want to remove that. So for that we are using this TensorFlow.squeeze, and cropping the images. Tiles also, when we are learning the tiles, we are cropping the images. So cropping the images to desired size. So such augmentation are also being done, and normalizing the images. Normalizing the images, the overall gray level being maximum being 256. We want the gray levels to span from -1 to +1. Usually we'll take from 0 to 1. Sometimes we'll take from -1 to +1 also. To have a zero mean centeredness, we take from -1 to +1, dividing by the center value 127.5, and -1. In fact, we want the ranges to span from -1 to +1. We are having this grayscale to RGB. That function called random.jitter. Random underscore jitter is used to convert from grayscale to RGB. So all these pre-processing we do. And coming to the data pipeline, we are having the data pipeline here, a train A, train B, as I have shown here, train A, train B, and all are here there in my Google Drive. And from there, I am taking train A directory, train B directory. So train A will be the training fundus images, and train B will be the training OCTA images. That has to be paired and learned. For this fundus, this is the OCTA. Likewise, it has to pair and learn. And the test folder also we have test A and test B. In fact, I have not opened the test A and test B. So there are other folders also. And this is only loading the names of the directories. And here we have the tensorflow.keras.utils image underscore dataset from directory. This is used to import the particular image files and load and stream those pipeline. In parallel pipeline, we are loading all those things under the different is train fundus, train OCTA, test fundus, and test OCTA. 43 files, 143 fundus and OCTA images for training, and 19 files we are used for testing. And remove batch dimension. Again, we are removing the unwanted dimension, the batch size, and all normalization and threshold SE block. All these things will be explained by our colleague Dr. Sambat Kumar. And coming to this is downsampling. Downsampling involved in the unit architecture. That will also be explained by Dr. Sambat Kumar. And coming to the main GAN, generative adversarial network. As I have already told, we have a GAN architecture with the generator and discriminator. That's what we are describing in the code here. We are describing the generator and the discriminator at this part of the code. generator underscore G, discriminator underscore Y. So I want to make it very clear. I am going to concentrate only on generator underscore G and discriminator underscore Y because that is only related to the project. So we have developed the code over complete. Okay, whatever is required for the project is only generator underscore G because that's what only generates the OCTA images. Okay, whereas generator underscore F generates back the fundus images that is relevant to the project. So generator underscore G it generates OCTA images and discriminator underscore Y. So what should the discriminator do? As per the explanation in theory part, discriminator should be able to discriminate between the synthesized OCTA images and the original OCTA images. So from the generator you have the synthesized OCTA images and here we have the real OCTA images. It should be able to discriminate between those two. So for that also X means fundus and Y means OCTA. So we are not concentrating on synthesized fundus. We are concentrating only on synthesized OCTA. We are not going back in the reverse direction. So will be strictly restricted to generator underscore G and discriminator underscore Y. So unit generator, we have used for generator part, we have used the unit generator with squeeze and excitation, with entropy based squeeze and excitation and all that. Those part and all will be explained by Dr. Sambat Kumar. And we have a fixed to fixed generator in the discriminator part. So that also will be explained by him. And now coming to the overall generator architecture, and this is what, as I have shown here, and I want to discuss about the different loss functions corresponding to the this thing corresponding to the GAN. So this is similar to the binary cross entropy loss, whereas this d of x corresponds to the original image, whereas z corresponds to the synthesized image. So the original image, when the original image is fed to the discriminator, and when the synthesized image is fed to the discriminator. So the first term corresponds to the original image fed to the discriminator, and the second term corresponds to the synthesized image fed to the discriminator. So G of Z. G of Z is means Z is a noise and forward what the generator synthesizes. So G of Z synthesized OCTA image. And what is the discriminator's output to the synthesized image? Whether the discriminator is able to identify it as a synthesized image or not. That is why this particular loss function here it has a direct term. Here it has a 1 minus term. So this is particularly to encourage the original input to the discriminator and discourage the synthesized input to the discriminator. So likewise, we program the loss functions here. Loss. What is the generator loss is nothing but TensorFlow dot ones like generator. So what this TensorFlow dot ones like will do is it will generate a tensor of ones that is equal in size to this generated image. So whatever is generated for that generator, we will have a tensor of ones like this. So first we will go to the discriminator loss. Yeah, first we will discuss the discriminator loss. What is the discriminator loss is done is for real images we have ones. We have ones compared to the real images, and we have zeros generated for the generated images. So the real images are labeled as ones, and the synthesized images are labeled as zeros. So whenever there is a mismatch, there will be a loss function. So both the terms are being added here. So total disk loss, that is being the discriminator loss. And when we come to the generator loss, here we are actually fooling the generator. So generator in the sense it is a synthesized image. So synthesized image should be taken as zeros, but we are putting a ones. We are putting as ones. So what happens is initially the generator loss will become very high. So after a certain period of time, to reduce the generator loss, what it will do is the generator will start synthesizing images that will look as good as the original images we are doing here. And after which we are having some identity loss also. What is this identity loss is nothing but how come the synthesized image is resembling the original image. Likewise, we are making some computation and we are taking the mean of the difference between the original image and synthesized image comes to training the model. When training the model, we are having different terminologies here. We have underscore y, fake underscore y in the sense synthesized image. Synthesized image. When we are feeding to the generator underscore g, we will concentrate only on the generator underscore. Why? Because generator underscore G is a generator that generates the OCTA images, whereas F generates the fundus image. We are not taking on to that. So the generator underscore G to the real X. Real X is nothing but what we can see what is term to represent the real fundus images. So X means fundus and Y means OCTA images. So for the real fundus images, what is this generator underscore G is going to do? What is my generator underscore G? Let me see. As I have told in the previous explanation, generator underscore G is a unit, whereas discriminator underscore Y is a pix to pix GAN. So for that, what is the output? That is called as a fake underscore y. So here fake is nothing but the synthesized OCTA image. I told y corresponds to OCTA image. So just similar to that, we have in the further part of the coding that we have discriminator real underscore y. So we have to skip certain lines. Okay. Discriminator underscore real y and discriminator underscore fake y. What is discriminator underscore real y is nothing but discriminator y. Discriminator y is the second discriminator that acts upon the OCTA images. Real y and fake y. Real y is nothing but the real OCTA images and fake y is nothing but the fake OCTA images. What is the discriminator's output that is taken here? Discriminator underscore real underscore y, discriminator underscore fake underscore y. And overall generator loss and overall discriminator loss we are calculating here. What is the overall discriminator loss is nothing but it is discriminator real underscore x comma discriminator fake underscore x. So we are not concentrating about x, we are concentrating only about the y. The overall discriminator loss will be discriminator loss of discriminator real underscore y. What is discriminator real underscore y? What will be the input to that? The input to that will be the original OCTA image, and the discriminator fake underscore y is nothing but the synthesized OCTA images. So what is the output of these two? That will be calculated as the loss. Already we know that the discriminator loss is nothing but comparing the real with 1 and synthesized with 0. So the code that is the generate underscore images, generate underscore G for sample fundus. Sample fundus, one fundus image we are taking, and that we are giving as an input to the generator underscore G, and how the image is being predicted is shown here. And this is the original image, and this is a predicted image done by our algorithm. And we have taken several images and we have estimated the mean square error also. Okay. So this is the original fundus image and this is a predicted image by our algorithm, whereas this is a ground truth. Ground truth is being taken from test underscore B. So train B, like train B, we have test B. So this is the ground truth. And this much our algorithm is able to identify. And what is the difference in the prediction? That is estimated as a mean square error. 0.17 is a mean square error. In that case, our algorithm is able to replicate up to 83 percentage. It is able to replicate the synthesized OCTA images.
Having generator as well as discriminator. So in a generator part, we have chosen unit. So the baseline unit. So here we have modified that unit with the help of some customized SE blocks. So first I'm going to tell you about unit. So this is a general left hand is a encoder path. Right hand side we are having decoder path. So in a encoder path, so here we are going to that is reduce the spatial resolutions for each and every stage by using this max pooling. Then by the same time we are going to increase the features by 2. So that is the resolution is off and the feature is increased by 2. So likewise we are going to do for each and every stage of the encoder. After that, which will be given to bottleneck layer. Then in a decoder path, we are going to revert back the resolutions, and that is by 2. Then after that, we are going to reduce the features. So at the last stage of the decoder, we are going to get back the desired output. So here our desired output is OCT, synthesized OCTA image, so which will be getting from the fundus image. So this is our aim. So this is the baseline unit architecture. So here what we have modified means, so here we see that orange color, that is here we are going to include one block. So that block is called as a blood vessel entropy based SE block. So with the help of that, we are going to get enriched vessels, blood vessels. So that is we are going to add it here. This is the basic architecture, and remaining thing as is, it is like baseline architectures only. So now let me explain about the code. So first I'll tell you about the unit generator. Then after that, we have added certain parts, that is like blocks. That one I'll tell you one by one. Okay, let me explain about the architecture of the generator. So this is our customized unit with entropy based SE block. So here we see I told you that is in a encoder we are going to do a downsampling. In a decoder section we are going to do a upsampling. So the downsampling we are going to done with help of the max pooling. Apart from that, in each and every stage of the encoder, we are having convolution blocks also. So this is that one. So here we are using 4 different stage of encoder. So this is the basic architecture of the downsample. So in the downsample, we are having 3 different convolution layers. So these are the first stage of the convolution layers. So here we are going to have a filters. So here in a first stage, we are going to start with the 64 filters. Then this is the kernel size of the convolution layer. Then here we are going to do the strides. So here we are going to choose the 2. So this is the first convolution layers. So here we are going to deal with the only 2D images. So that's why we have taken convolution 2D. Then after that, here we are having normalization. So generally we are having 2 different normalizations available. That is batch normalization as well as instance normalization. So for each and every year, we are having only very less number of images for training as well as testing part. So that we are doing normalization with the help of instance only. Instant in the sense each and every image for resolution based. Second layer like that we are going to have filters, then kernel size, then strides. Say here we are going to reduce the strides as a 1. Then here also we are calling either batch normalization or instant normalization. So this is the general representations. So whenever we have done training, so we have done with both batch normalization as well as instant normalization. So we got good output when we have chosen instant normalization. So that is why here we have mentioned both. Then this is the third convolution layers in the encoder stage. So here also we have filters, size, strides. Then at the end of this third layer, here we are going to call the entropy SE blocks. So this is our novel block. So here instead of that normal SE block, so we have taken the concept as a entropy per channel we have taken. Then after that, which will be computed by using the formula. Then after that, here which will be scaled with the help of the attention mechanism. So this is done for each and every stage of the encoder. Then this is the general encoder block. Then after that, in a decoder block, we are doing upsampling. So this is like a reverse of the previous one, that is downsample. In a downsample, we have max pooled. Here we are going to upsampling. So we are going to bring back this that is spatial resolution as it is. So that's why we are going to do it here. So that we are going to call convolution 2D transpose unit generator. So in the generator, we are having 2 stacks called down stack as well as up stack. So down stack we are calling by downsample functions 4 times, so that we are going to get a 4 stages of the encoder. So the first stage we are going to have a 64 filters. Then second stage we are going to have a 128. Third stage we are going to have a 256. Fourth stage we are having 512. So that much features we are getting, so that we are going to get a depth feature map in the encoding part after completion of the fourth stage. Then which will be given to the bottleneck layer. Then from the bottleneck layer, which will be again passed into the decoder stage. So in a decoder stage, we are having 3 stages. That the fourth stage has the first stage of a bottleneck, so which will be available here. So this is that fourth stage of the decoder part. Then the remaining 3 stages, as we are going to bring back our original spatial resolution, as well as we are going to reduce our depth features by off. So this is exactly reverse of the encoder stage. So that we are going to have upsample 256 in this second stage. In a third stage, we are going to have a 128 filter. In a fourth stage, at last, we are having 64 station block. So as already told you, instant normalization means which will operate only for one image. So here you see, it is like AC block. So we are having skews and excitation. In a skews, in a normal AC block, we have done that is they have done with the help of global average cooling. So here also we are going to have the same thing. Then from that we are going to get a feature maps per channel. Then which will be activated. That is in a standard SQ block. So what they have done means per channel they are going to get a feature map. So which will be multiplied by the original images, right? So here also we have done the same. So we are going to squeeze with the help of the entropy. Okay, so that is why here entropy is calculated. So that attention will be given based on the entropy, not like max pooling, so that we are going to get some enhanced images like in a prediction image we have seen some good images, right? So that is with the help of that entropy based AC block only. So this is the entropy. Then we have calculated entropy. Then the same entropy is to be converted by 0 to 1. Then which will be scaled with the help of the original features, so that the entropy is multiplied by the attention. Then finally we are going to get a recalibrated future maps. So which is we are getting from this block. So that one will be passed into. So here we are going to get that recalibrated weights. So which will be passed into the decoder block with the help of the skip connections. So why we need this skip connection means that is without losing our spatial resolution. So we want to get information. So that's why we are going to pass this skip connections. So with the help of that, we are going to retrieve back our original informations without losing any spatial informations. GAN. So here we have developed a front end. So the same thing only we are going to give it to doctor. So in a local machine. So this is developed by the Flask framework. So this is the same as our blocks, necessary blocks what we have developed. So instant normalization as well as that customized SC block. After that we have called that unit also. Then after trained, so here we are going to, that is after the training, so we have saved our model. So the same model here we have called. So here you see, so this is our model we have saved. Then the same model only we have given here, so that whenever we are going to see in a local host, so that we are going to upload an image, then we will get a corresponding OCTA synthetic image and paste it in our browser. So this is an app which is created by ourselves. So this is the IP address link. So here this is our web page. So here you see, click or drag and drop to upload one image. So the namely fundus image. So I'm going to upload one fundus image. So I've already uploaded. So after that we need to generate the corresponding OCTA image. So here you see, so that I'm going to click the same, upload and generate. So this is our image, synthetic OCTA image for the corresponding OCTA image. So if suppose we need to download the image means we have an option here. So to download the same.